Hudson Golino, and I'm here to share a very comprehensive overview of our AI-GENIE methodology. I just wanted to point out that we have 323 slides for this course. So, and only 2 days, so it's an extremely intensive workshop. And we'll be talking about more how the workshop works, how it will be, the pace and etc. In a moment. So let me just open the presentation here to make it easier for us, and then we can get started. I would like to thank every single one of you that's here with me today and with Laura. We are extremely excited to be sharing our work with you and to help you and train you how to use the methodologies we have been developing. So the workshop is divided into 5 parts. Today we have 3 parts. So we will start talking about scale and task construction, an overview of a very traditional approach. In the second part of the workshop today, I will be giving a very quick introduction to AI and large language models. And then we'll be discussing AI-GENIE in specific and all the building blocks of AI-GENIE. On Thursday, Laura will be presenting the AI-GENIE R package that we have been developing. She has been the main creator of the package, and also we will share with you all the details on how to use the package and several examples, and we'll have hands-on activities on Thursday.
Welcome to a new phase in the history.
So I prepared this AI video summarizing the workshop for you guys. So please let me know if you can hear the sound, if the sound is okay.
Welcome to a new phase in the history of psychometrics and assessment. Introducing generative psychometrics, the revolution of artificial intelligence in scale development. First, hello everyone, and welcome to our workshop on automatic item generation and validation, a network integrated approach using LLMs in the free and open source R programming environment. Today, we're exploring something truly revolutionary in the field of psychometrics, how artificial intelligence is transforming the way we develop and validate psychological scales. For decades, creating high-quality psychological assessments has been a resource-intensive process. It typically requires teams of expert psychometricians, multiple rounds of testing, and months, if not years, of painstaking work to generate items, analyze their psychometric properties, and refine them into valid, reliable instruments. But what if I told you that artificial intelligence and generative psychometrics could help us accomplish much of this work in a fraction of the time? That's exactly what we've been exploring with our AI-GENIE approach, automatic item generation and validation via network integrated evaluation. By combining the capabilities of large language models with advanced network psychometric techniques, we've developed a methodology that can generate hundreds of high-quality, theoretically grounded assessment items, automatically identify and eliminate redundant items, evaluate item stability and dimensionality, and produce structurally validated assessment tools with minimal human intervention. Our research has shown that this approach not only saves tremendous time and resources, but also produces scales that perform as well as traditionally developed instruments when administered to real participants. Throughout this workshop, we'll dive deep into this methodology, exploring the 5 parts of our presentation. Traditional scale construction approaches, an introduction to artificial intelligence and large language models. There are AI-GENIE framework. There are AI-GENIE R package, and practical examples you can apply in your own work. So let's begin our journey into the future of psychometrics, where artificial intelligence is opening new frontiers in psychological assessment for automatic item development and validation in silico.
All right. So let's keep going here. Before we can get started, just a quick notice of proprietary rights and limited use. So in the slides, you can find here the notice. So basically, we are asking to not share or use anything that's in the slides because that's proprietary. And the package, it's free for research projects and non-commercial usage, but it cannot be used for free for commercial purposes. And Laura will talk more about that on Thursday. All right, so let's get started with a motivating example. So there is this very interesting paper which makes a literature review of pathological narcissism and narcissistic personality disorder. So the definition of narcissism, according to this paper, led by Pincus and Lukovitsky in 2010, is basically one's capacity to maintain a relatively positive self-image through a variety of self-affect and field regulatory processes, and it underlies individuals' need for validation and affirmation, as well as the motivation to overtly and covertly seek out self-enhancement experiences from the social environment. So the authors, they suggest that there are two types of narcissism, one that's normal and one that's pathological. So in their review, normal narcissism can support adaptive functioning, achievement, motivation, and ambition, contribute to self-esteem and well-being by increasing personal agency and several other positive characteristics. However, pathological narcissism, on the other side, involves significant regulatory deficits and maladaptive strategies to cope with disappointments, show difficulty handling threats to the positive self-image, is associated with functional impairments and distress, has higher psychiatric comorbidity, and is characterized by two main dimensions: narcissistic grandiosity, so inflated self-image, entitlement, exploitative behaviors, and narcissistic vulnerability, depleted self-image, shame, interpersonal hypersensitivity. So for Pincus and Lukovitsky, pathological narcissism, the normal and the pathological one, they are distinct constructs rather than the opposite ends of a single continuum, as the absence of pathological narcissism does not necessarily indicate the presence of normal narcissism. So there are two dimensions of pathological narcissism: grandiose, so the characteristics or attributes of grandiose pathological narcissism is repressing negative self-other representations, distorting, disconfirming external information, entitled attitudes, inflated self-image without corresponding accomplishments, fantasies of unlimited power, superiority, perfection, interpersonally exploitative acts, lack of empathy, intense envy, and aggression exhibitionism. The vulnerable dimension is related to depleted or enfeebled self-image, self-criticism, shame, depression, interpersonal hypersensitivity, social withdrawal, suicidality, rage responses to criticism, avoidance of relationships, and difficulty maintaining self-esteem. So the question I bring to you guys is, how would you develop and validate a new instrument to measure pathological narcissism? You can respond in the chat, or you can just unmute yourself and respond here. What steps would you take to develop and validate an instrument, a new instrument for pathological narcissism?
Just this is Shauna speaking. Just design items that target both of the dimensions, and refine the items. And you would need to pilot the items, and then conduct factor analysis, on and on.
Yeah, that's a great overview, Shauna. Thank you for sharing. That's basically the summary of a broader methodology that we have been using for more than 100 years in psychology. So let's view an overview of traditional scale and task construction approaches that we have been using in psychometrics and psychology and related fields for more than 100 years now. So there are several interesting books and manuals talking about test development and validation and the processes. I would just point a few. Maybe one of the most well-known is the book by Deborah Bandalos, Measurement Theory and Applications for the Social Sciences. She has a very interesting chapter explaining the steps of scale development. There is also the Handbook of Test Development with several summaries and guidelines. We have Psychological Testing by Teresa Klein. In terms of validity theory, we have Keith Marcus and Danny Borsboom's Frontiers of Test Validity Theory, and of course, Rod MacDonald Test Theory book, and etc. So the literature in this field is just huge and historical. There are many interesting things. But if you look at all the books published, all the guidelines by the APA, by the International Test Commission, and so on and so forth, we can divide the process of developing and validating new measurements, new scales as follows. The first step, and the most important first step, of course, is the conceptualization of the construct and the definition of the construct. So we need to clearly define the construct we're going to measure, including the theoretical background and in having an operational definition. So the step involves establishing a clear and precise understanding of the concept and attribute being assessed. The second step that helps this first one is doing a thorough literature review to evaluate existing measures and theories to justify the need for a new instrument. The goal is also to identify gaps, limitations, and opportunities for improvement in current assessment tools, or identify lacks in the theories, in the previous theories, and ways forward. Okay, once we have this conceptualization done and the literature review done, we start with the most laborious part of the process, which is the item generation, so writing the items. So originally, or traditionally, we need to generate a very large pool of items based on the construct definitions. So this involves creating a wide range of potential test items that align with the intended measurement objective. And then usually we get expert reviews. So we ask experts in that domain, in that construct, for feedback regarding item relevance, item clarity, content coverage. And usually we employ around 5 to 10 subject experts. And based on the feedback we receive from the experts, we do the first round of item revision, and we improve the items, or we modify the items based on the qualitative feedback from the experts, addressing quality, clarity, alignment with the construct definition. Once we have done that part, that takes a very long time and lots of effort, we go to the first step of pilot testing. So pilot testing involves several different steps, depending on the construct, depending on the approach the person is using, but can be summarized as follows. So we identify a representative sample of individuals from the intended population to participate in the pilot testing. Ideally, most of the time, people just use convenience sample. We administer the tests or the scales to pilot them and to collect their responses. We do some preliminary item analysis. We ask the participants to provide feedback and to review the items so we can gather information about the clarity and the understandability of the item wording. And then we do an initial round of psychometric analysis, usually searching and trying to understand the structural validity of the instrument, item dimension stability, the factorial structure, item quality, and so on. So once we have implemented this first round of review, we can do several things. We can explore the underlying dimensions, see if the dimensions match the expected dimensionality structure given the theory or given the theoretical background that were used to justify the item construction. We can check the fit of the structures using confirmatory factor analysis or generalized structure equation modeling. We can assess reliability of the items. And then based on the initial analysis, we can refine the scales, refine the items, and collect more data. So when we are collecting more data, usually in the second round of data collection, or if you have a big enough sample for the pilot testing, you are interested in several different types of validity. So the validity evaluation is an umbrella evaluation in which we will seek to verify the content validity. So it's the expert judgment on relevance and representativeness of the measurement instrument, the construct validity that demonstrates that the instrument measures the intended theoretical construct, criterion-related validity, so that can demonstrate the instrument's ability to predict future outcomes. That's what we call predictive validity, or correlate with existing validated instruments measuring the same construct, what we call concurrent validity. We can see how our new instrument diverges from similar constructs, but they are not the same construct, using structure equation modeling or confirmatory factor analysis, and so on and so forth. There are several psychometric guidelines that can be followed. It's a process that has a very rigorous, specific, scientific-based development set of guidelines with validation, interpretation, and several rounds of analysis until we have an instrument that has enough evidence of validity, different types of validity, to be used for research or to be used for making inference about how human beings operate in the world. But everything I said costs money. Nothing is for free. Either will cost the money of the experts developing or writing the items or reviewing the items, or it will cost money collecting data. So let's revise a little bit the monetary costs of scale development and item development. So there are different types of expenses that are incurred depending on the phase in which we are in the item development or scale development process. But we can have an idea of how expensive it is using the average cost per item index in item production. So the average cost per item can vary significantly, ranging from several hundreds to over $1,500, depending on the stage of the item development process. So we have to pay people to generate the items for us or to write the items for us if we're not experts in that domain. We need to pay experts to revise the items. Of course, the larger the item pool, the more money we're going to spend with experts reviewing and revising and refining the items. Then we have editing. We have money that we spend in the experimental tryout or in the pilot study or in the initial pilot studies if you need more than one. And then there is publishing, et cetera, et cetera. So the costs are usually divided into the item development cost. You have administrative fees, processing, and data analysis costs. It varies depending on the complexity of the items. And you also have the problem of item attrition. So items might become outdated, have security risks, be lost during the tryouts, or you discover in the middle of the process that one item that everybody thought was excellent is not working well in terms of psychometric characteristics, et cetera, et cetera. So another way to evaluate the costs for scale development and item development is the cost per testing event, which in my opinion is the largest chunk of cost. So the cost per testing event involves paying people to answer the items or the scales, paying administrative fees for companies that are collecting the data, especially if you want national representative samples, testing seed time. So the longer the instrument, the longer the scale, the more money you need to pay each participant, and so on and so forth. So let me just give you one example. So 30 minutes of testing for a nationally representative quota sample using systems like Prolific or Bilendi, which are companies that I use when I'm doing data collection, will cost you around $10,000. So that's a very short amount of time, only 30 minutes of testing. 1,000 individuals, nationally representative quota sample will cost you $10,000. So now imagine that we're developing a new scale and we are following a very, very rigorous item development, scale development process with several rounds of testing. So we start with a pilot testing with only 1,000 people in a nationally representative quota sample. And then we refine the items, we revise the items, we find the initial evidence for validity, dimensionality, etc. We change things, and then we do a second round of testing, but this time with revised items. We are collecting data in 2,000 individuals. And then after we collect all this data, we have a second round of refinement, and then we test again in 2,000 people, all nationally represented quota samples. If we are taking only 30 minutes of test seed time, that will escalate to $50,000 to develop a new scale. If you're really using a very large nationally representative quota sample divided into multiple stages, it's a lot of money. So the cost per item can range between $500 and $2,000. Or we can develop new scales with few cents using AI-GENIE. And that's why your guys are here. And that's what we're going to be talking. So in AI-GENIE, all you need is the first part. You need the construct definition. You need to have a good idea what you want to measure. And then what you're going to do is you're going to feed our AI-GENIE package the trait definitions. So for example, if we want to develop our items, a new scale to measure pathological narcissism, we have two traits that we're going to evaluate according to the theory: grandiose narcissism, and then we have the trait definitions there, vulnerable narcissism, and then we have the definition of the construct there. For each one of these constructs, for each one of these dimensions, we'll have different attributes. We'll be talking more about that later on Thursday, but the attributes are basically the first order factors or first order communities of your instrument. So if grandiose narcissism is a general factor or a general trait represented by specific traits of repressing negative self-order representations, distorting, disconfirming external information, lack of empathy, intense envy, exhibitionism, for example, and vulnerable narcissism is a general trait or a domain with the specific subdomains depleted or infeasible self-image, self-criticism, and shame, for example. We can provide examples of items for each dimension, and that's all we need. And then we just use the AI-GENIE function to generate new items for us. And at the end of the process, we'll have a new scale. Here's the one example with the final version of the instrument that I generated using AI-GENIE. And then here we have the EGA structure. EGA stands for exploratory graph analysis. We'll be talking about that in a minute. And we identified 4 communities that are similar to factors. One is a community related to interpersonal insensitivity and self-focus. The other one is attention-seeking and grandiose exhibition. Both communities 1 and 2 here represented by nodes red and blue in the network represents grandiose narcissism. Community 3 and 4, self-critical and harsh self-judgment, and vulnerability, shame, and sensitivity, represented by communities green and orange, are part of the vulnerable type of grandiose narcissism. So we developed a new scale, and we can talk about the evidence of the quality of the items and the dimensionality structure later. But basically, not just we have a new scale with a dimensionality structure that works extremely well according to our theory, but both the items and the dimensions are extremely stable, and that's what we want to have when we have new scales, and I'll be talking about that in a minute. That's just to exemplify and to give you an additional motivation to learn what we're going to learn today. Okay, now let's go into how we can do that. What are the building blocks of the methodology that we use to go from just the definitions of the traits and examples of items to automatically developed items and validation in our computers without having to collect data in humans. And to do that, we need to talk about artificial intelligence in large language models. So to talk about artificial intelligence in large language models, we need to talk about natural language processing. So natural language processing is the ability of a computer to understand, interpret, and analyze human language. So techniques from natural language processing involves doing sentiment analysis, doing text summarization, doing machine translation, and many other things. So natural language processing is a field that addresses various ways in which computers can deal with natural, in other words, human language. And this field has a very interesting story. So it starts in the 50s with the early days of natural language processing. And natural language processing was extremely influenced by the early days of computation. So computer science inspired this field, and the researchers believed in the 50s that all you needed to do very high-level natural language processing tasks in a computer was to understand the rules of language and program these rules in the computer. And then the computer would be able to do linguistic tasks to a similar level of capacity as humans. As you know, it didn't work. It worked for very specific problems, specifically for querying information, creating relational databases, and doing very specific type of analysis, but it didn't went so far. In the 80s, we're moving 30 years ahead of time. Statistical learning was basically created or developed, and the field of machine learning emerged very, very strongly. So we have the first few machine learning algorithms or statistical learning algorithms in the 80s, led mainly by researchers from the University of Stanford and other universities. But one of the main names of the early days of statistical learning was Leo Breiman, that developed the classification and regression trees algorithms and bootstrap aggregating trees and random forests, just to give a few examples. So when the field of machine learning emerged, or the field of statistical learning emerged, then what people started to do was, okay, let's use these super effective predictive modeling techniques combined with text data and see if we can improve natural language processing tasks. And it worked very well. It exploded the capacity to make computers understand human language. But 10 years later, we have the first big historical thing that happened that really pushed the field forward. The World Wide Web comes along, the internet is born, and then eventually we have all sorts of information that used to be stored in books or printed in printed formats, being now available in this internet, in which people could not just access information, but generate new things and put them in a web page, for example. That basically generated a huge amount of text data to be analyzed, right? Not just text data, but high level, high quality text data that could be analyzed with the new machine learning approaches. With the advance in computer graphics, specifically for game playing, what the industry did was they discovered that they could generate even more complex and interesting 3D scenarios for games if they relied on graphic processing units, or GPUs. GPUs then started to be used and developed for game playing and for improving the quality of the scenes of the games. But what the researchers discovered is that GPUs are extremely fast at matrix multiplication and matrix operations. So if GPUs are extremely fast at matrix multiplication, matrix operations in general, they started to say, okay, what happens if instead of using CPUs in our computers, we start to use GPUs, graphical processing units, to process even larger types of matrices, for example, from neural networks. And then it was discovered that we could do neural networks much faster if we use GPU processing, and that combined with machine learning approaches, it really exploded after 2010, the capacity to analyze text data and to do natural language processing using neural network approaches. At around this time of 2010, we have a number of breakthrough developments in neural networks, specifically with what we call today deep neural networks. And if we move forward about 7 to 9 years, we have new breakthroughs, theoretical and mathematical breakthroughs that enabled deep learning networks to really deal with language in a way very similar to what humans do. So, and that comes what we call the transformer model architectures. So before we talk about the transformer model architectures, let's see some examples of natural language processing tasks that are very interesting. So check those two phrases. John wrote a letter with a pen, and John saw a pig in the pen. So what is the difference between pen in the first phrase and pen in the second phrase? Can you unmute yourself or just write in the chat? Context. All right. Can you explain more, Gina?
If I understood the question correctly, it's what's the difference between how the use of pen here in a sentence, and it's due to the context, right? So one context is, the letter. So if it's letter, then I'm assuming it's pen as in a writing pen, whereas the other sentence is the context is pig, and therefore pen is attached to, yeah, if that makes sense.
Yes, excellent. That's right. Yeah, so the first one, John wrote a letter with pen. We know that pen is a writing instrument because we understand that it comes with a specific linguistic context. And the linguistic context is, if we're paying attention, is letter, right? So letter combined with pen make us think in writing instruments. In the second phrase, John saw a pig in the pen. The linguistic context is pig, as you said very well. And then when we combine pen with pig, we will interpret pen as being a animal enclosure, a space where we can put animals sorry. And that's exactly correct. So pen is a noun in both phrases, but what makes pen different from the first phrase compared to the second phrase is the words that are together, right? What we call the linguistic context of the words, right? So if pen is closer to letter, because letter is in the phrase, there is a few possibilities left for us to understand what pen is. Pen must be a writing instrument, right? If you know English, so the assumption here is you need to know the language. You can associate pen and letter and then understand it's a writing instrument. The same thing for the second phrase, an enclosure for animals, because we know that pen is associated with pig. But the problem is, we as human beings, we're awesome, we're excellent at understanding linguistic context if we know the language. That's the assumption. We need to know the language. If I start speaking Portuguese here, you guys will not be able to understand. Maybe a couple of you will. I think Simval is here. Simval speaks Portuguese. And who else speaks Portuguese? Maybe a couple of other people here, Joanna, might be able to understand because they speak Portuguese. But most of you don't speak Portuguese, you can't understand. And you can't understand because you can't process the information you're listening to, right? So the first thing we need to assume is that the language, you know the language, so you can understand the inputs. But also, once you know the language, you need to have knowledge about the world, right? If you read both phrases for a 9-month-old baby, the baby will not be able to make any kind of differentiation. The knowledge about the world is very limited. But I'm just diverging. Let's go back to the problem here. The problem here is we are very good at understanding linguistic context, but computers are not, or computers were not good at understanding context. And what is the objective definition of context? So the objective definition of context is the collection of words that are in the phrase. So as we saw, John wrote letter and pen is very different from John saw pig and pen. If we're paying attention to pen in both phrases, we know that John wrote a letter. It's giving us the context. It's giving us all the information we need. John saw pig is also giving us all the information we need about pen, right? So it's the collection of words and the position of the words in the sentence. We need both. Actually, nowadays we discover we don't need both, but that's something for later. But originally, in natural language processing with transformer model architectures for large language models, it was discovered that we needed both the collection of words that came together in a phrase and the position of the words in the phrase to be able to understand context. So context awareness was a huge problem in natural language processing since 1950s up until around 2017, 18, and 19 with the proposition of the transformer model architecture of deep neural networks by Google. So context awareness is in natural language processing is a very recent development. And everything depends on how we represent language. We understand language by many different ways. We can hear, we can read, we can see, we understand the social context, but computers are more limited. Computers understand numbers. So for us to be able to solve natural language processing problems in a computer, we need to take whatever input we have, if it's text or if it's images or videos, whatever, we need to make a first translation. The translation that needs to be made is from the input, words, images, whatever, to numbers. And that's where embeddings come into play. So what is what we call word embedding? So a word embedding is an ordered vector that numerically represents the meaning of a word, or as we say in the field of large language models, the meaning of a token. So side note here, when we're talking about tokens in natural language processing, specifically in large language models, we're talking about words, phrases, sentences, or entire documents. It's any piece of linguistic information. How big, how large, how detailed is this piece of linguistic information is decided by the user. But usually when we're talking about tokens, we're talking about units of linguistic information in a sentence, which means words and punctuations. So usually a word embedding is a ordered vector with hundreds of numbers. So it's how we translate the words into numbers so computers can understand. So because it's an ordered vector of numbers, it forms what we call high dimensional space. That's a math lingo for a collection of numbers that have many numbers. So here's some examples of word embeddings and traditional representations. So for example, if we project these high dimensional vectors into a three-dimensional space, we can see, for example, that the words man and woman are closer in this three-dimensional space, that walking and walked are closer in the three-dimensional space, and so on and so forth. So initially, the word embeddings that were generated by the field of natural language processing, they were good for querying and retrieval in documents, but they could not be used for many other things. So they were not super useful at the end of the day. But the problem is, not the problem, the solution is that the traditional word embedding methods, they evolved to incorporate the self-attention mechanisms from the transformer model architecture, and then they became much more useful than they were initially. So this figure here represents a very interesting evolution of word embeddings. So here in the left, we have what we call a traditional word embeddings from an approach we call bag of words approach or BAL model. So basically, we have different words or different tokens, I, run, fast, and we represent each word or each token as a collection of numbers, right? That's the traditional bag of words approach. That's what everybody understands when we talk about embeddings. It's just translating words into numbers. But as you can see here in this figure, there is no relationship between them, right? Each word has a specific collection of numbers, and that's it. We can project them in a three-dimensional space, see how closely related they are, and that's it. When the first long short-term memory recurrent neural network models were proposed, word embeddings evolved to something a little bit more sophisticated. So now we don't have only the words being translated as a high-dimensional vector of numbers, but now we have also some kind of context, linguistic context, embedded in these embeddings. So here we have I run fast because the recurrent neural network, the embeddings that are generated here, they carry information about the three words I run and fast. But it was really with the proposition of the transformer models and large language models that embeddings became context rich, which means that embedding models from the transformer model architectures, part of the large language models area, they carry all the linguistic information about which words are together and the position of the words in the structure of the sentence. So when we have the words that are together, the position of the words, we can understand the meaning. We can translate what we human beings are very good at, which is reading, understanding the context, and making associations between words, as we did with the John wrote a letter with a pen example. But now we can do that mathematically. We can represent the words, we can represent the sentences using numbers, but the numbers now carry the contextual linguistic information with them. So they're much more useful for doing tasks in natural language processing. So there is a very, very good book about natural language processing with the transformer models, published by Louis Tonsval, Leandro van Verra, and Thomas Wolff. And this book has an excellent introduction to the main definitions of deep neural network architectures with the transformer architecture. Here, what I'm going to do is I'm just going to briefly mention some elements of these deep neural network architectures, so you guys can understand my vocabulary when I make specific comments related to each one of these components. So one of the important things about these deep neural networks with the transformer architecture is that they use backpropagation to improve their internal representation. So backpropagation is a method that basically computes the difference between a target label and a model prediction that's propagated back through the network to update the weights and the biases of a neural network. Basically, imagine that we are trying to predict the word that comes next. So we have a phrase, John wrote a letter with a, and then we want to predict the next word, the next token. And we have a collection of documents, and we can train a neural network to make the prediction for the next word. And imagine that the next word it predicts is something other than pen. And we want the network to predict pen. So if it predicts something other than pen, there is a difference between what the prediction was and the actual label, the target label. The target label in this case is pen. So we can take this difference and bring it back to the network through a backpropagation method that will update the weights of the neural network and will increase the likelihood of predicting pen the next time. These neural networks, these deep neural networks, they have what we call hidden states in them. So this is the representation of an input if it has been passed through the model. So the information of the original input is maintained, but is represented in a different way inside the network to make predictions. I'll show you some examples in a minute. These deep neural network models with the transformer architecture, they can be classified into very different types of models. And the models usually, they differ in terms of what kind of blocks they have on them. Most models, some models are encoder-only models. Some models are decoder-only models. Some models are encoder-decoder models. And now we'll explain the difference now. So what is an encoder? So encoder or an encoder block. An encoder block processes and transforms the data into a meaningful numeric representation. So imagine that we have a translator. So I'm speaking in Portuguese. The translator knows both Portuguese and English. So when I say something, the translator will take what I said, will hear the words, will understand what I meant with my words, will organize its meaning. So that's what the translator is doing. This is what encoder blocks do in deep neural transformer architectures. It takes the inputs, it organizes the inputs, and it understands the meaning of the inputs. And then we have decoder blocks. The decoder blocks, they take the outputs of the encoder blocks and they generate new representation or new predictions. For example, in our analogy, we have the encoder taking the Portuguese words, understanding the meaning, representing the meaning, and then is going to translate, give this meaning to the decoder. The decoder is going to take the translator's meaning derived from Portuguese and provide the meaning, the same meaning in English. What is crucial in this process, specifically when we're talking about natural language processing with computers, is that both the encoder and the decoder understand what to pay attention to. For example, in our example, John wrote a letter with a pen. You guys, when I prompt you guys to think about the meaning of pen, you immediately pay attention to wrote and letter. How can computers do the same? Computers can do the same thing with what we call the self-attention mechanisms. So the self-attention mechanisms, they are basically going to take the encoder block information. So remember, the encoder block organizes and understands the meaning of the input, represents it numerically into different hidden states of the neural network that's represented by these black boxes here in this figure. And then the decoder block will take the inputs from the encoder and then will transform it to something. But the thing is, the decoder block needs to do something. It needs to pay attention to what are the most important elements in the inputs, just like as we did. John wrote a letter with a pen. When I ask you the meaning of pen, you pay attention to wrote and to letter. So the self-attention mechanisms will do exactly that. So what is the definition of attention in a transformer model architecture? So attention is the weighted importance of inputs of tokens or states that the model prioritizes for prediction. And this became extremely famous in natural language processing and in science in general after the publication of the extremely influential paper called Attention is All You Need, that was led by Ashish Vaswamy from Google Brain. This paper has only almost 200,000 citations, and it was published in 2019. So what is attention? So attention, what Google Brain did, what Google did, was they discovered a way to represent attention mathematically in deep neural networks. And that's why it was so groundbreaking. So attention is quantified in deep neural networks with transformer architecture as a mathematical transformation of three types of matrices, what we call the query matrices, the key matrices, and the values matrices. So queries are basically the relevant information that is the current state of the encoder or the decoder block in the deep neural network. Keys are the information available to attend to. So it's basically elements of the input, like the embeddings, numeric representations. And the values are linear transformations of the input or the information to be extracted.